we present an all-glass, compression-dominant polyhedral bridge prototype and its form finding and fabrication. The recent development of three-dimensional graphic statics using polyhedral reciprocal diagrams has greatly increased the ease of designing complex yet efficient spatial funicular structure forms, where the inherent planarity of the polyhedral geometries can be harnessed for efficient construction processes. Our previous research has shown that we can use 1 cm annealed glass to make hollow glass units, which have considerable load-bearing capacity. And it's also feasible to use the hollow glass units to construct a 10-meter span double-layer glass bridge. This modular approach can greatly simplify assembly and construction of a large scale. This paper presents a smaller bridge prototype to address the challenges of the larger bridge regarding form finding, detail developments, fabrication constraints, and assembly logic. The compression-only prototype is designed for prefabrication as a modular system using PolyFrame for Rhino. There are 13 hollow glass units in this prototype, and they can be prefabricated and assembled on site. The form finding of the bridge starts with constructing a force diagram of a single-layer funicular bridge. The force diagram of this glass bridge is made by extruding a 2D aggregation of polygonal faces to a point where the 2D polygonal faces determine the bridge topology as well as applied load distribution, and the extrusion height determines the bridge rise and internal force magnitudes. The total area of the faces maps to the total applied load of 1 kN, and the area of each face maps to the magnitude of the tributary load on the corresponding node. By changing the areas of the polygonal faces, the distribution of the applied load can be manipulated. After having the single-layer funicular form and force diagrams, the double-layer form can be derived by subdividing the force polyhedrons of the single-layer form. The force diagram is subdivided in a way that all the interfaces between the polyhedral cells are as perpendicular as possible to the force flow, so the sliding can be prevented. Next, we start to materialize the bridge by adding details to the base geometry. Each cell has one top face, one bottom face, and several side faces. The top and bottom faces are materialized as deck plates using 9.5 mm annealed glass. For the side faces, there are two different types, one facing the neighbor polyhedron cell and another exposed to the outside. For the side faces that contact the neighboring cells, the side plates with the male and female locking mechanism are developed to enforce the connection between the adjacent hollow glass units, which need thicker and irregular glass. For the other side faces exposed to the outside, since no locking mechanism is needed, the same 9.5 mm annealed glass is used. For the side plates with male and female connections, the irregular glass parts have to be customized as there's no off-the-shelf product available. KILN casting is chosen to be the fabrication method. To make the fabrication and production easier, the profiles of the male and female side plates are standardized so that all the male side plates share the same master shape and all the female side plates share another. Therefore, only 2 molds are needed for KILN casting. The fabrication process is greatly simplified. The cast glass pieces will be cut into target shapes using WATERJET cutters. Within each hollow glass unit, the deck plates and side plates are held together using 3M VHB tape. Between each pair of neighboring hollow glass units, a transparent plastic interface material is placed between the male and female connecting parts to avoid local stress concentration. Then, a small-scale model experiment is carried out to investigate the structural performance of the 2.5-meter bridge. Since the form of the bridge is designed based on one specific load case, its behaviors under other load cases need to be examined. The test result shows that the bridge is most likely to buckle from a concentrated asymmetrical load. In all cases, the bridge model successfully bears an applied load of more than 15 times of its self-weight, which shows a good potential of load-bearing capacity. A finite element analysis is still needed to rigorously simulate the behavior of the full-scale prototype. Later, one hollow glass unit from the bridge is chosen to explore the fabrication and assembly methods. For the KILN casting of the master shapes of the side plates, 2 sets of one-time mold are developed using silica and plaster, and 1-inch float glass is used as the cast material. A 5-axis abrasive WATERJET is then used to cut the cast glass into target shapes. Special connection clips and bars are devised to chew the assembly to the required geometric tolerance. The connection clips in Figure A are 3D printed using PLA, and the connection bars in Figure B are cut with a CNC milling machine using 6mm HDPE sheet. The assembly of one hollow glass unit can be done in less than half an hour. Here is the fully assembled hollow glass unit and the detail of the transition corner between the male and female side plates. The experience gained and errors found in this trial fabrication and assembly will help us adjust the workflow. In the future work, the fabrication of all hollow glass units and the assembly and construction of the whole bridge will be continued. Thanks for watching.